Hi everyone. Today in this lecture, I want to start chapter 15. Chapter 15 is about filters, but this time our focus is on active filter. Before going forward, let's see what are the differences between a passive filter and active filter. First, I'm going to start with passive filter. So if I'm talking about a passive filter, it means that I'm making the circuit, I'm making my filter using R, L, and C. So I'm only using passive components such as inductor, capacitor, or resistor to make the filter. Consequently, because I'm only using passive element, the maximum gain that I might get is equal to 1. It means that it's impossible to amplify the input signal. So the best case scenario is that we can have the exact same magnitude at the output of our filter. So the maximum gain is equal to 1 and the amplification is impossible. Another characteristic of passive filter is that if you add a load, the load can change the characteristic of the filter. You saw that in the last examples of chapter 14. So adding load can change the characteristic of the filter, such as omega C or gain. So the cutoff frequency can be affected. The gain can change if we add a load to a passive filter. Another feature of passive filter is that if you want to make a band pass filter or a band reject filter, for both of them, you need to have inductor. So in order to make a band pass filter or a band reject filter, having inductor in the circuit is necessary. You know that for these two type of filters, you need to have an RLC circuit. So it's impossible to avoid inductor, which is heavy, large, costly, and it introduces electromagnetic field. So it's not really convenient to have inductor in the circuit, but if you want to make a passive filter, a passive band pass or band reject filter, it's impossible to avoid inductor, which is not the case in active filter. And the last feature of passive filter is that there is no obvious method to make the filter more ideal. So the last comment that I would like to add here is that no obvious way to make the filter better and closer to ideal situation. So these are the features of passive filter that we discussed in chapter 15. Now let's see what are the characteristics of active filter. An active filter has active element. So the first feature is that it includes active elements such as op-amp. Now you might ask why we call op-amp as an active element. The reason is that it has external power supply. So this particular element has some external power supply which makes it an active component. So the active filter has both passive and active components. So it can have op-amp in the circuit and still we are allowed to have resistor, capacitor, and other passive component as well. The next feature of active filter is that it can eliminate all the disadvantages of passive filter. The first one is that we are not limited now to a gain equal to 1. So the gain can be higher than 1 because we are working with active component with external power supply. The second feature or the second advantage of active filter is that we can load the filter without changing the filter characteristic. So it can be loaded without any change in characteristic of the filter, such as omega C or gain or other feature. The next advantage of active filter is that no inductor is required for band pass filter or band reject filter. So as you saw in previous slide, if you want to have a band pass filter or a band reject filter with passive component and with a passive filter, you cannot avoid having an inductor. But if you are working with active filter, then you can avoid using inductors. And the last feature of active filter, or let's say the last advantage of active filter, is that by cascading very simple filters, you can make higher order filter, and those higher order filter are closer to ideal situation. So you know the steps on making your filter closer to ideal. So by cascading, simple filters, you can make higher order filter which are much closer to ideal situation. Okay, now let's take a look and analyze the circuit of a first order low pass filter. Here you can see the circuit of a first order low pass filter. In this circuit we have an op-amp. This op-amp has an input impedance which is equal to R1 and a feedback impedance which is the equivalent of R2 and C in parallel. So this is a first order low pass filter, but in order to analyze this, I want to remind you that how the transfer function of a low pass filter looks like. So if I have a low pass filter, the standard form of the transfer function, h of s, should be something in the form of k multiplied by omega c divided by s plus omega c. So what I want to do is that I want to analyze this circuit and see if I can get a transfer function between output and input voltages that follows this particular transfer function. Now in this circuit, my output is the voltage, the output voltage here. So here is my output signal, which is the output voltage, and I do have my input signal as VI, which is the voltage of my voltage source. So knowing that this is the transfer function, the standard form for a low pass filter, it doesn't matter if I'm using a passive or active circuit, the transfer function of low pass filter is always something in this form. Now I want to analyze this circuit and see if I can get the same transfer function. Before going forward, I would like to remind you how we can describe and how we can analyze an inverting amplifier circuit. Here you can see an inverting amplifier circuit. In this circuit, we have an input impedance equal to Zi, an output and another feedback impedance which is equal to Zf. So if we have something in this configuration, then the relationship between your output voltage, which is Vi, and your input is in this form. So your VO is equal to minus ZF, or your feedback impedance, divided by ZI multiplied by your VI. So we call this an inverting amplifier because of this negative. And the gain of this amplifier is equal to the ratio between ZF and ZI. So if we choose this ratio to be greater than 1, then it can amplify the input voltage. Now, knowing this equation, we can easily solve the circuit that you saw here. Obviously, in this circuit, my input impedance is R1 and my output impedance is R2 in parallel with C. So let me write the relationship between VO and VI in this circuit. So what I'm going to do here, I will describe the relationship between the output voltage and input voltage, which is equal to minus ZF over ZI. I know that ZF is R2 in parallel with 1 over CS in Laplace domain, and my ZI is just one resistor, which is equal to R1. So I'm going to have R2 multiplied by 1 over CS divided by R2 plus 1 over CS. This is what I have for the parallel equivalent of R2 and 1 over CS. I have the negative here and R1 in denominator. I will combine them, and I'm going to have minus R2 multiplied by 1 over CS divided by R1 multiplied by R2 plus 1 over CS. Now, I'm going to multiply everything by CS here to get rid of this denominator, and my transfer function, obviously what I have as VO over VI is the transfer function of this circuit. So by multiplying both numerator and denominator by CS, I'm going to have minus R2 divided by R1 multiplied by CS R2 plus 1. Now the problem is that I don't want to have any coefficient for S in denominator, because then I can describe the transfer function in its standard form. So what I'm going to do is that I'll divide everything by C and R2, which are the coefficient of S here. I'm not going to touch this R1 because that's going to be my gain. So I'm going to rearrange my transfer function in this form. I will keep minus R2 over R1 out because that's just a coefficient. And then by dividing both numerator, which is now 1, and denominator, which is 1 plus R2CS, by the coefficient of S, I'm going to have 1 over R2C in numerator, and in denominator, R2C will cancel out the coefficient of S. So I'm going to have S plus, and then if I divide 1 by R2C, I'm going to have 1 over R2C. So now you can see that this transfer function is exactly in the form of the standard format of low-pass filter transfer function. And it tells me that the cutoff frequency for the circuit is equal to 1 over R2C. So I have the cutoff frequency here, and then what I have in numerator should be equal to the gain multiplied by the cutoff frequency. So since I have the cutoff frequency here as well, it means that what I have left here is basically the gain. So let's go back to the circuit. The circuit that we have here is a low-pass filter because its transfer function is equal to minus R2 over R1 multiplied by 1 over R2C divided by S plus 1 over R2C. So here we have the cutoff frequency, and then we have the gain of K here, which is equal to minus R2 over R1. So this filter that you can see here is a first order low pass filter, and it has a cutoff frequency which is related only to the RC components you have in your feedback impedance, and the gain is the ratio, the negative of the ratio between the feedback resistor and the input resistor. So these are all you need to know about a first order low pass filter. I want you to notice that a main difference between passive and active low pass filter is that in spite of passive filter, the gain and omega C are defined independently here. So it means that you can choose to have a particular cutoff frequency, and it only depends on the values that you are selecting for your capacitor and resistor in your feedback configuration. And then after you've selected your cutoff frequency, you can choose whatever gain you want to have by changing the ratio between R1 and R2. So you can just play with your R1 and change the gain. So something that is very important here is that K and omega C are defined independently. Let's draw the frequency response plot of our low pass filter, our active low pass filter, but this time I would like to draw it in as Bode plot. There are differences between frequency response plot and its Bode plot, and the first one is that when we are talking about Bode plot, we have logarithmic axis instead of linear axis, which provides a wider range of frequency. So the first characteristic of Bode plot is that we are looking at logarithmic axis instead of linear axis for omega. So this way we have a wider range for frequency. And the second difference is that instead of looking at magnitude of H at j omega, so this is our gain. Instead of looking at our gain, we would like to look at 20 log base 10 of our gain. So it's going to be 20 log base 10 of H at j omega. So we are looking at logarithmic axis for frequency, and on the other axis, which we have our gain, we would like to look at 20 log base 10 of H of j omega. So if we are looking at a frequency response plot, then what we have here is omega, and what we have as our gain is the magnitude of H at j omega. Now, if I want to draw the Bode plot related to this frequency plot, what I have to do is that I have to use logarithmic axis for omega here. So here I'm looking at a linear axis, and here I'm looking at logarithmic axis. And the gain axis is going to be described based on 20 log base 10 of H at j omega, the magnitude of H at j omega. And remember that we call this as our decibel gain. So this is the standard gain that you're looking here, and its equivalent decibel gain is basically equal to 20 log base 10 of this magnitude that we are looking here. So this is going to be our Bode plot. And these are the interesting things about decibel gain. So if we are focusing on decibel gain, which is 20 log base 10 of the magnitude of H at j omega, then what will happen is that the decibel gain will be equal to 0 whenever the magnitude of H at j omega is equal to 1. So if you have a gain equal to 1 and a standard gain equal to 1, which means your filter is not amplifying and completely passing the signal without any change in the magnitude, then its decibel gain is going to be equal to 0. So if you want to find the same gain on the decibel plot, you have to look at a decibel gain equal to 0. Why? Because if your magnitude is equal to 1, then you know that the log base 10 of 1 is equal to 0. Something else that you should be careful about is your cutoff frequency. We talked about cutoff frequency, and the cutoff frequency is basically equal to 1 over radical 2 multiplied by the maximum gain. So if you apply 20 log base 10 to this equation, then you're going to have 20 log base 10 of the magnitude of your h of j omega c, your cutoff frequency, equal to the 20 log base 10 of this term. Now you know that if you're working with a logarithmic function and you have multiplication, what you can do is that you can consider this as addition. So it's going to be 20 log base 10 of 1 over radical 2 plus 20 log base 10 of your h max. Now, this is a nice representation of how you can find your cutoff frequency. This term, 20 log base 10 of 1 over radical 2, if you calculate this number, because that's a constant number you have in front of your logarithm. So if you calculate this, you're going to have minus 3 decibel. So it's telling you, in order to find the cutoff frequency, what you have to do is that this is your decibel gain, the maximum decibel gain. You have to decrease the maximum decibel gain by 3 decibel, by minus 3 decibel, and that's going to be your cutoff frequency. For example, let's assume that this is your Bode plot. I want to know what is the cutoff frequency. What frequency is my cutoff frequency? So what I have to do according to the equation I have here is that I have to find my maximum decibel gain. So let's assume that the maximum decibel gain, for example, is equal to 10 dB. Now, according to this, the decibel gain at cutoff frequency, so my decibel gain, let me use another color. So the decibel gain at omega c is equal to the decibel gain at maximum gain minus 3 decibel. So if my maximum gain is equal to 10 decibel, then I have to focus on 7 decibel, and the frequency that I have a gain equal to 7 decibel is basically my cutoff frequency. So in Bode plot, in order to find the cutoff frequencies, what I have to do is that I have to focus on the maximum gain, and then by decreasing this gain by 3 decibel, so by these 3 decibel, I can find the cutoff frequency, and the cutoff frequency is going to be the frequency that this value of decibel gain happens. Okay, now let's do a quick example for low pass filter using active element. So let's assume that we want to design a low pass filter, and we know that the available resistor for R1 is equal to 1 ohm. We want to see what should be the values for R2 and C in order to have a cutoff frequency equal to 1 Hertz and maximum gain equal to 1. So I know that my maximum gain is equal to 1, so it means that H max is equal to 1. So its decibel equivalent is equal to 0 decibel. So if my maximum H of j omega is equal to 1, then its equivalent in decibel form is equal to 0. So I have a maximum decibel gain equal to 0. So it means that if I want to know what is supposed to be my cutoff frequency, then my cutoff frequency is going to be minus 3 decibel. So this is how I can find the cutoff frequency on Bode plot if I have the Bode plot. However, the purpose here is designing the circuit. So here I know that the cutoff frequency of a low pass filter is going to be 1 over R2C. And the gain is equal to minus R2 over R1. So we know that R1 is equal to 1. Now it means that if we want to have a gain equal to 1, then R2 should be equal to 1 as well. So we can figure out what should be the value of R2 based on the gain that we need. And for C, we can find that from this equation. So omega is equal to 2 pi f, and that's equal to 1 over R2C, in which R2 is equal to 1. So it tells us that the capacitor value should be equal to 1 as well, because 2 pi f is equal to 1, and your C should be equal to 1 in order to have a low pass filter which has a maximum gain equal to 1 and the cutoff frequency equal to 1 as well. So our H of S for this filter is going to be minus 1 over S plus 1. So it has a gain of 1, it has a cutoff frequency equal to 1, and if I draw the Bode plot, the maximum gain is equal to 0 decibel, because the gain is equal to 1, so that's equal to 0 decibel, and then it has a cutoff frequency equal to 1 as well, so here I have minus 3 decibel. So it has a Bode plot similar to this.